So then the next one is going to be on another classification topic that is going to take a closer look at linear classification, as we have done. And then it's going to propose an extension to that, which you can think of as pre-processing the features in such a way that the method becomes much more capable. And that's called the support vector machine, which is a pretty famous method. And but we're going to learn a few other things along the way. And so the motivating example in this unit is starts to get more into, you could say, image processing. In particular, we're going to be looking at handwriting recognition, where what we are given is a picture of a digit. In this case, it's going to be a simple example. It's going to be a digit somewhere between 0 and 9. And here you can see many different examples of these digits. And we would like to be able to recognize which digit it is. So basically, it's a classification problem. The features are going to be given to us as a little 28 by 28 image. And there's 10 classes. There's going to be 70,000 examples in our database. And this is the famous MNIST dataset. It was originally collected in the 1980s with the goal of eventually having the male readers be able to read the zip codes on envelopes instead of having to have humans transcribe them. And so, this was done quite a while ago, but this data set is still very widely used in machine learning courses. Its size is big enough to be, you can do sophisticated things with it, but small enough that it's not incredibly taxing. It has an interesting number, 10 classes, and the feature dimension, there's 28 by 28 is 784 pixels per image. So again, this is relatively simple, it's widely accessible, and there's many benchmarks. People have been working on this for decades, I guess, so there's lots of examples of how well different classifiers work on this. So this is easily downloadable, almost built in. It's you can get it in scikit-learn in a couple of lines. So here's a table that just gives you an example of how different methods perform. So here's the error rate in the right column. So this is an example of a linear classifier. The error rate here is 7.6%. And then we have a really simple 2-layer neural network, 1.5%. And we have some decision trees. We'll talk about that in a few units, 0.87%. And here we get to support vector machine, 0.56%. So you can see it's pretty good. It's not the best that can be done. You can see here there's other techniques with neural networks, or actually committees of many neural networks all working together with particular pre-processing. They can get down to maybe 0.2. But the point is that support vector machine is pretty good. It's getting down to close to as good as you can do on this data set. So it's part of our motivation for looking at it. Okay, so we just have to start with some basics. How do we deal with images in Numpy? So as humans, when we look at the image, we want to look at it as a two-dimensional grid of pixels like this. Basically, the pixel values in these what we call grayscale images, black and white images, they go from 0 as black all the way up to 255 as white. These numbers are set so that you can describe each pixel with an 8-bit integer. So you don't have to, it's not like you have to save floating point, double floating point precision. This is enough. And but when we deal with these things on a computer, it's often more convenient to have them as just a one-dimensional array. So we can do that just by reshaping in Numpy. So there's a couple ways of doing this. So if I have this 28 by 28 array and I want to expand it into a vector, I can use this dot ravel, or I could also do reshape -1. So the -1 in Numpy is a way of saying fill in the right value for as many pixels as we have. Here, essentially, you're telling it, reshape this down to one dimension. I don't need to tell you the number of elements to use because you know already how many total elements we have. Now, if you have this one-dimensional structure and you want to go to 2 dimensions, then you have to tell it how many to use. There's another option. You could, if you want, write 28 comma -1, and then it would know, okay, I want 28 rows, and the number of columns is as many as I need to fill in all these values. So that would also work as having a -1 there. So there's a couple options as how you do this. So ravel is just a way of vectorizing, as is reshape -1, but then when you come back, you have to tell it a little bit more information on how many rows and columns you want. Okay, and another comment is that when we do this vectorization in Numpy, as opposed to other languages, Numpy is going to be done by stacking rows, not by stacking columns. Typically, when you read papers or books, the convention in making matrices from vectors or vectors from matrices is that you always work column-wise. So for example, if I want to take this matrix and I want to express it as a vector, I'm going to take these values, and then underneath them, I'm going to stack those values, and then underneath them, the next column, and so on. And so this will be the final place, and then so we'll finally have, at the end of this long vector, we'll have this. But in Numpy, what you do is you actually take the first row, and then you append to that the next row, and so on until the last row. So you build it row-wise. So that's just something to note. If you don't know that, maybe you get surprised when it's not working the way you think. And so you could say that Numpy works according to this convention as long as you replace the x above with x transpose. And then that's how Numpy works. All right, so how do we plot things? Well, matplotlib is the most popular package for plotting within Python. And matplotlib has, for plotting images, it has this imshow command. And you just tell it, you give it the matrix, the array, and then you have to give it a color map, basically said to tell it how it maps values to colors. And so here we're just saying use a grayscale. So it's going to give us a black and white image. And so we're creating this little plot digit function that essentially takes a vector x, reshapes it into a matrix of the right dimensions, calls imshow, and then we're also getting rid of the axis ticks here that would otherwise be there. And that's essentially what our little plot digit function does. So when we extract the data from the structure mnist that we downloaded, the dot data gives us the features, which are these. It's going to give us a matrix where every row is the vectorized version of one of these. And then it's going to give us a set of labels. So these are digits between 1 and 10 for every one of these images that tells us what is being represented. So what we can do is we can select some random digits from our data set and plot them. And to get that randomness, we're going to generate this permutation. This is a vector of indices between 0 and 70,000 minus 1, and it's going to be randomly permuted. That's what this I-perm is. And we're going to use this, like we can look at the ith index into that randomly permuted vector. That gives us our image, our data set index, and then we can plot the digit by extracting the ith row of that feature matrix, and then up here, converts it to an array and plots it. And so this is just a random sample of 4 of these MNIST digits. And as a human, you look at this and, yeah, this is a 7381, no big deal, right? But some of them are not so easy to classify. Even a human is going to make mistakes. So, so that's where we want to see if how machine learning does and whether we can do even better than a human. Okay, so our first example in this direction, we're going to use multinomial logistic regression because this is what we developed in the last unit. This is our best method so far. Just to save a bit of time, we're going to train and test on only 10,000 samples. Even though we have 70,000, we're only going to use 20,000 of them. And this is just because, as we'll see, once you get to this data set of this size, it takes a little bit of time on your computer. And so we're just going to be a little bit impatient and work with this smaller data set in the demo. We're going to do, for cross-validation, we're going to split our data just once into a training fold and a test fold. We're not going to do k-fold because, again, that takes a little too long on this data set for us. So here we're setting number of training, number of tests to 10,000. Also, we're going to do some pre-processing. We're going to do, it's not exactly standardization in the way that we've defined it. What we're going to do is we're going to take our features, we're going to divide by 255, so that will scale them to between 0 and 1. We're going to multiply by 2, now they're scaled between 0 and 2. Subtract 1, so now they're scaled between minus 1 and 1. So they're not going to be zero mean exactly, they're not going to be unit variance exactly, but this is a common processing method for images, is to apply the same scaling to every pixel. If we had applied our standardization as we had learned before, the problem with that would be that we would have a different mean and variance for every pixel. And the problems that could cause is pixels that are, let's say, over here are probably close to black always. And so if you try to standardize them, I don't even know what would happen because the variance could be 0 for some of those pixels, but even if not, essentially what would happen is after you standardized, this would look very gray. And you wouldn't really be able to make out the foreground and the background as easy. So we want to apply the same normalization to every pixel, not different ones for different pixels. And so that's part of what this is doing. Okay, so I'll highlight this. Okay, and then as you can see, there's other ways to do this. There's some scikit-learn functions that can do this also, but here manually what we're doing is we're taking the first 10,000 values in our permutation vector, and we're giving that, we're creating the training samples from those, and then we're going to take the next 10,000 values in our permutation vector. We're putting those in our test quantities. Okay, so now we set up our linear regression model. We're going to tell it use multinomial rather than one versus rest. We're going to tell it to use this solver because it's a relatively fast one. We're going to cap the maximum iterations at 500, and we're going to use a pretty small value of this penalty for our ridge regression, and fit it, and let's see what happens. So, number one, when we compute the accuracy, we get an accuracy of about 90%, so error rate about 10%, which, if you remember that table, is not very good. It's not terrible, but certainly it's I think the worst one on the table was like 7.5% or something like that, so it's not as good as that one. And when we look through to find a few examples of where we made errors, you can see here, like this one, the true one was 9, it estimated as 1. The true one was 4, it estimated as 8, and so on. This one is maybe the hardest, but still I think that a human would probably not make mistakes on these. So the question is, why is multinomial logistic regression not doing so well? Can we do something to improve it? So to understand why it's not working so well, let's just think again about what exactly is happening in multinomial logistic regression. So this is what we do to classify a test vector, in other words, an MNIST image. So we make these class hypotheses. In this case, we'd have 10 different classes. For each class, let's assume that we have designed some weights. So we have an intercept term and some weight coefficients here. And these are going to classify the sample X as either in class K or not in class K. So when we apply these weights to the sample, we're going to get a score for class K. And then we're going to essentially look at the largest value of ZK across the different Ks, and that's going to tell us the class that we're most confident that this X fits into. And even though this is not necessary for the actual prediction step, the way that we train this classifier is that we think of the score as telling us the probability that the sample is in class K given X. And the particular model that's used in MLR is that probability mass function has this form called the Softmax. So this is going to give us a vector of different values of the probabilities that they'll all sum to 1. They'll all be between 0 and 1. And as such, these are elements of a probability mass function. So essentially, the whole point of this is converting these real numbers into probabilities. And those probabilities are a little bit easier to interpret, although they're not necessary to do the classification. The real numbers themselves, you just find the largest one, and that's how you set your score. Okay, so this is how we can visualize everything in a picture. We start with our test image. We convert it to a 784-dimensional vector. Then we do this matrix multiply. We have here a matrix of weights. Every one of these rows, or let's say the kth row, contains the weights for class K. So we do this matrix vector multiply. We add the intercept terms. We get our score vector. Again, this is going to have different elements, one for every class. And if we want to think about these as probabilities, we can put those elements through the softmax. But we just look for the largest index in this vector, and we say, that's the class that we believe that this is in. Okay, so that's our method. Let's take a look at the weights that are learned by multinomial logistic regression. Okay, so how can we visualize the weights? Well, let's think about, this is the equation that we use to get the kth score. So you can see that there's going to be this intercept term, but the really important thing is happening here. We're taking this inner product between X, the image, and the weights. Another way you can think about this is you're multiplying every pixel in X times the corresponding pixel in the weight matrix, and then you're adding them all up. So what you want is that, if I'm trying to look for, let's say, class k equals 0, I would expect that this weight vector responds to 0 pictures very actively. So if I put in a 0-like picture here, that I get a big response. And so when you look at, here we're actually plotting these weight coefficients as a matrix. You can see, oh yeah, I can see that there's sort of a 0 shape within there. So in this picture, gray, like the value 0.5 would be gray. The value, let's say, close to, larger than, sorry, I said that wrong. A value of 0 in the weight vector is going to be assigned a color map value of gray. Positive values here are going to be assigned white or closer to white, and negative values here are going to be assigned closer to black. So that's how we're visualizing this. And when you look at this, you can see, yeah, if X represents a 0 digit, and I do this pointwise multiply here, what's going to happen is these positive values here are going to multiply against my large values in X, and they're going to give a large positive response. And then the negative values here in the middle are going to be sort of saying, okay, if X has any positive stuff here, it's probably not a 0, so it's going to be, negatively weighting stuff there. And then it's going to be saying, well, the stuff on the outside, I don't really expect anything to be there, so I'm just going to set. But maybe if someone drew a big 0, I don't want to discount it, so it's going to just set those values to be 0. And so that's what happens with the 0 class. What happens with the 1 or the 2's class and so on is similar. You can see that the weights for the 1's class look kind of like a 1. The weights for the 2's class look kind of like a 2. And then you have a 3, and then you have a 4. And so things are working well, but what's interesting is that this is what happens when you have 100 training examples. Once you look at the full 10,000 training examples, pictures are a lot more complicated. So you can kind of see a 0 shape. It gets more complicated here. Can you see a 1 shape? It's hard to say. I could see many shapes in here, I think, depending on what I want to see. Maybe there's a 2 in there, maybe there's a 3 in here, and so on. But essentially what's happening, and this is kind of explaining what the problem is. What's happening is that MLR is struggling to match all the training examples from in each class, because there's many variations within each class. There's many ways that people are drawing their 1s and their 0s and so on. And if you have 100 training examples, there's not so many different ways. But once you get to 10,000, you have all these different weird ways. And this one classifier is trying to learn all of these. And essentially, what can happen is that it can get distracted by some of the easier examples to classify, and it's not focusing so much on the harder ones. And this is a little bit reminiscent of that imbalance problem that we saw when we talked about logistic regression, where we said, why does least squares not work well as a cost? Because it's getting distracted by the easy examples, the ones that are far away. And in fact, you could say, even though MLR was a big improvement, it too has a little bit of this issue where it is not focusing all of its energy on the ones closest to the boundary, but it's actually focusing some energy on ones that are far from the boundary, which perhaps it shouldn't get distracted on. And this is actually our motivation for the methods that we're going to learn about in this unit, the support vector methods. They're going to focus exclusively on the samples that are close to the boundary, and they're going to completely ignore the ones that are farther away. So that's going to be the big difference between the new methods and the ones from the previous unit. Okay. So one other point is, even though these pictures look messier, as you get more samples, the classifier definitely does work better. It's not like it's getting so confused by these samples that it's working worse. It's just that when we look at what it's trying to do, we can get some insights into how we can improve the method. All right. Any questions on anything so far? Okay, great. So I think we've done enough for today, and we'll continue with some more details next time.